Hello everyone! Today we're going to be solving a kinetics question, in particular one that deals with curvilinear polar coordinates. So these can sometimes be a little bit tricky, but the one at hand here isn't too bad. So let's give it a shot. Let's see what we can do here. So what do they give us? Well, we have this shape here, this horseshoe looking shape. And we have this fixed point. And then we have this object that pivots around, and has some motion. And at the end of there's this ball. Perhaps I didn't draw this clear way. There we go. And there's this ball here, right? So it's easy to imagine that this ball is going to move. More specifically, this ball is inside this horseshoe shape. So as this spins, this ball is going to slide down and up this rod and stay within that horseshoe. All right, it's pretty straightforward. And they have defined in the question this angle theta right there. And they gave us the direction of motion is going to be that direction. What else do they tell us? They give us an equation of motion r, and they say that r is 0.6 cosine 2 theta meters. And then they say that is point P. So what else do they give us here? They say that the mass is 0.1 kilograms. I'll just read you the problem. It says 0.1 kilogram pin P is constrained to move in the smooth curved slot, which is defined by this equation here that I've written down. Its motion is controlled by the rotation of the slotted arm, which they're calling OA, although I won't write down those points, which has constant clockwise angular velocity given by theta dot equals -3 radians per second. Determine the force on arm OA, or determine the force arm OA exerts on pin P when theta equals 0 degrees. Alrighty, so let's see what we can do here. So I sort of have a systematic way that I go about solving these problems. I have several steps that I follow. Step 1, maybe not the wisest step, but it's just kind of mindlessly writing down the acceleration formula for these, or equation rather, and its acceleration equals the acceleration in the radial direction, and that component looks something like that, plus the acceleration in the theta direction, which looks something like that. Bam! Check. Did the first step, mindlessly wrote down equation. All right. Second step for me is now's the time where I think about it and just figure out, all right, what's happening? So best way to do that is with a free body diagram. So we have this ball here, whatever you want to call it, pin at position P, and it tells us, I believe, that it's on a vertical plane. So because it's on the vertical plane, we know that gravity is actually going to be a factor here, or as if it was on a horizontal plane, gravity would not have been a factor, but it is, so we're going to have a weight. There's also going to be a normal force, and remember, we're not evaluating at the point shown in my picture, but rather we're evaluating at 0 degrees, which is right right there. So which direction the normal force is, I'm not sure, nor does it really matter. It will get sorted out just by solving this problem. But it does appear that it is horizontal. So I'll draw that to be the normal, just like that. Any other forces? Any other forces? Speak now, forever hold your peace. Well, that's a normal. That's a normal on the horseshoe, from the horseshoe. But then there's also a force, another normal exerted by the rod. So perhaps I'll call that normal rod and normal H maybe for horseshoe. All right, and then the coordinates are important here. So the ER, the radial direction, is the distance from a fixed point. So in this case, the fixed point is at O, right? And it's this distance here. So the fixed point is R, so it's R distance away. And when that's at 0 degrees, we know that R is actually going to be in this direction. So we have ER, and we know that the theta direction is 90 degrees away, and the motion is going clockwise, so it must be down. So there you go. We have a proper free body diagram now. Alrighty. So I could sum the forces at this point, although then we're going to have to do some kinematics later. I say we do the kinematics first. So let's get that out of the way, shall we? So let's actually solve for this R double dot, R dot, and all that jazz, right? So the problem says its motion is controlled by the rotation of the slotted arm, which has a constant clockwise angular velocity. So the angular velocity is always constant. Therefore, the acceleration of that velocity, or the change in that velocity, the acceleration, the angular acceleration, or alpha, whatever you want to call it, is 0, right? So then we can just simply say R dot, and remember that R dot is a time derivative, right? So that's the same as saying dr dt, right? So if I was to take the derivative of this given function up here, what would I get? Okay, I would get 0.6 sine, keep the inside, and it's a derivative of cosine actually gives you a negative, so I'll throw a negative in there. And we got to multiply that by the derivative of the inside, which is 2 theta dot, like that, which is equal to negative 1.2 sine 2 theta, and all of that is multiplied by theta dot, which I can directly plug in right there. Alrighty, so then we have our double dot, which is just that there. So how do we do that? So that's a constant. So -3 times -1.2 is positive 3.6. Negative remains. A derivative of sine is cosine 2 theta times that derivative of the inside again there, or we could plug in that -3 again, and that will give us -6. -6 times 3.6 is 21 21.6 negative, of course, and then that's cosine 2 theta, like that. And is that everything? Well, then we need theta, of course, because we only have the change in theta. So this theta is just going to be negative 3t. Okie dokie. I'm happy with that. Where theta that we're told is 0 at that time, so that would imply that the time is 0 at that time, but the time isn't really much of a factor in this problem, so I'll just write theta equals 0. All right, now let's write some good old sum of the forces, huh? So sum of the forces in the y direction, right, gives us mass times acceleration equals, weight's actually the positive number, but weight minus normal r. The acceleration in the e theta direction is this 2r dot theta dot. So I can say mass equals 2 r dot theta dot. All right, so what is r dot? Well, if I plug in 0, we know that sine 0 is, well, 0. So that whole term is actually 0. So that's just going to make life easy, and we're just going to write that as W, or weight, is equal to nr. So that's some handy dandy news that mg equals nr. And now we can write the sum of the forces in the x direction is equal to negative nh, which is equal to ma, where a in this case is going to be this term here. R, plain old R, is going to be, it looks like 0.6. Squared, it looks like that's going to be why am I doing math? I hate math. No, I don't. Okay, negative 3 squared is negative 9, or just 9. What's wrong with me? Times r, which is 0.6, and then r double dot is negative 21.6. So 21.6 minus the 5.4 is 20.27, and m is 0.1, so I'll just go ahead and write that as 2.7. All right, that was a struggle. That was more of a struggle than it should have been, but that's okay. Equals negative nh. Alrighty, well, now we have a bunch of stuff, right? That doesn't immediately seem super related to each other. So what's our goal? Our goal is to find nr, right? And we just said that nr equals mg. I'm an idiot. So 9.81 times m 0.1 times 0.1, that equals nr. So nr equals 0.981. Yeah, I don't know what's wrong with me. I lost sight of what the problem was even asking for, and I did all that crap. So this problem is easier than I thought it was, evidently, because all you had to do let's solve this NR value right there. So there you have it, y'all. Sorry for taking y'all everywhere. I guess ideally we would have solved the problem with going and mapped it out a little better, but you know, everything worked out. Everything worked out. There's the answer. Pretty simple question. It can get complex. The trick is just draw your free body diagram. Remember to write your equation here. And there's really not much more to it. The hardest part of these problems is with the coordinates and drawing a proper free body diagram. This problem, of course, super easy, but harder problems that involve psi get much more complicated. So hope this was helpful. Sorry if it was long. Shouldn't have been long, obviously, but is what it is. See y'all in the next one. How about that?